Hi everyone, thanks for tuning into my talk today. I'd like to start by thanking Frank and the team at MemVerge for creating this forum and for hosting the event this week. And I also want to say happy St. Patrick's Day to everyone who's celebrating it this weekend. I'm James Corcoran, I'm from Stack Research, and my talk today is going to be on measuring AI. Split into three short sections. The first is I'm going to talk about the case for self-hosting versus API calling. Second, how to think about sizing and scaling LLM infrastructure. And the third is a look at hidden performance levers of LLM systems that we've been digging into here at Stack. So, self-hosting versus API calling. I thought I'd start with a quote from a guy called James Vincent, who wrote a really interesting book on the history of measurement throughout civilization. And he says that the closer we look, the more the world reveals itself. And I thought that was a good launch pad for this part of the talk. I think we've all seen a chart like this over the last few months, laying out the performance improvements in LLMs over time, and whether or not you believe that the trajectory here is exponential or that it's going to taper off and become asymptotic. The direction is clear. Everything's moving up and to the right. LLMs are getting better and better over time. They're getting more and more capable over time. But I am reminded of this book from John Maxwell called Talent is Never Enough. And I think the point is that in the infrastructure world, our job is to create the right platform, the right operating environment for these LLMs, as capable as they are, to be able to do their best work and to get to the best outcomes. So the question of whether to host an open source LLM and manage it ourselves versus call an API in the cloud, we put together this really simple rubric, pros and cons of API calling versus self-hosting. Very intuitive. With API calling, the pros are that it's quick to set up, you've got lower initial cost, and you've got access to cutting edge models. The cons are that you've got less control, you've got data privacy concerns, and very limited customization. And then you've got almost the mirror image in the self-hosting scenario. You've got control over data privacy, you've got potential cost savings at scale. We're going to dig into that in a lot more detail over the next couple of slides. And you've got a whole range of customization options. On the flip side, you've got higher setup costs. You need to invest in infrastructure, expertise, and ongoing maintenance. So let's look into some hard data around this question of whether to self-host or call an API. And ultimately, what we're trying to do here is arrive at a break-even analysis. This is not about getting to a magic number that a lot of the LLM quality benchmarks promote. I think most benchmarks out there give you one number, and that gives you an indication of sort of the goodness of the model. This type of analysis is more involved, it's more detailed. There are several parameters and levers that you can push and pull to impact the performance of LLM systems. And that's what we're trying to analyze here. So I'll take you through the numbers. We've got a couple of different workloads, a short context workload and a long context workload. We're measuring median reaction time, response time, and output rate. And we're, of course, measuring that in self-hosted environments and versus APIs. And then we're measuring that against a range of different lambdas, which is the first column. So what's lambda? Lambda is the average number of prompts hitting the system per second. So you can see in the short context scenario, we're varying between 30 and 46 prompts per second. With long context, where 0.7 to 1 prompts per second. And then we're computing the ratio of performance, the self-hosted versus the API. So what can we say? I could say that self-hosting systems generally outperform APIs, but that APIs are significantly more cost efficient in the baseline case. But probably the most interesting statistic to pull out here is that we were able to observe a lambda of 5.98, or call it 6 prompts per second, whereby a particular self-hosted platform was able to match the performance of a leading API. So that self-hosted platform was, well, roughly 2.7 systems running 8 H100s each, at about 37% utilization. In other words, if your workload is scaling beyond 6 prompts per second, and you've got a system of roughly this magnitude, three 8-way systems, and the case for self-hosting and self-managing your LLM grows. The other interesting thing about the data that we collected here is that API performance varies significantly, both inter and intraday. And there are variations in terms of latency, throughput, and fidelity. And fidelity is an important metric that we track in our benchmark. It's measuring the truthfulness or faithfulness of a model to a ground truth that we set at the start of a run. And so we can say that we're observing differences in both the performance, efficiency, and output of a model. But if you run it on a Monday versus a Tuesday, or if you run it in the morning versus the afternoon. So those variations, we're continuing to dig into them at the moment, and we're going to be dropping a research note in the next couple of weeks that lay out that data. So next we move on to sizing and scaling LLM infrastructure. We set out by asking ourselves, these 6 questions. Can the system keep up with human reading speed in real time? It's really important for user experience. How does performance vary with context size? What's the max request load before performance drops? How does the system scale with users? And when should we add GPUs? What's my cost per word? And how much energy does the system consume in the data center? And in search of those answers, we measure metrics in these 4 broad areas. We're measuring response time, output rate, words per dollar, and dollars per inference. And we do that for a given lambda. Remember where lambda is the average number of inference requests arriving per second. And as we vary that lambda, we can observe variances in response time, output rate, words per dollar, and dollars per inference. And that's what makes it really interesting. So how do we measure these metrics? This is a picture of the setup. SUT here stands for system under test. It's the entire stack, so the storage, the compute, the network, and the memory. We have a fixed set of data and a set of prompts. We load them into memory. We have a system which then interactively streams those prompts to an inference engine based on that all-important lambda. And we measure several timestamps along the way. We're measuring timestamp of the prompt, the timestamp of the first byte we receive back, or time to first token, as it's called, and the timestamp when the full response is completed. Of course, we're doing that over the course of a full run and several runs. We collect all of the data, write it out to disk, and then we are able to draw charts like this. So here we're comparing the question length to the response length. Whereas I like to think of it as how good is an LLM at listening versus talking. And what we can see is that longer contexts generally lead to longer responses, but that the relationship isn't linear. So it does suggest that the model has a sweet spot for context length. And it's something that AI engineers are probably going to want to dig into, perhaps if they are building guardrails that wrap around user prompts and user input. Important to understand how those guardrails can potentially impact the quality, fidelity, and output profile of a set of responses. Next, we look at the response time over time. So what we want to do is pinpoint when the system starts to become sluggish. We're going to push it to its limits and see when it gets slow at processing our prompts. This is going to help us think about how and when we need to start scaling the system, adding more GPUs to the system. So I'll talk you through the scatter plot. We've got three different runs. We're looking at them side by side. The y-axis on the left-hand side is latency, so lower is faster. And the y-axis on the right-hand side is the total number of characters processed in both the prompt and the response. And what we observe, and it's reasonably intuitive, is that the shorter the text that is processed, the faster it gets processed. And that's why we can see clusters of the dark blue circles along the bottom of the scatter charts. But we can also see some of those dark blue circles bubbling up to the top of the scatter chart. And that's where the system starts to become sluggish or slow in its response. And the important thing here is that we're observing this pattern, which appears to be repeatable across the three different runs. So it's not random data or random behavior in that sense. That correlates, of course, to the queuing stats that we have along the bottom. So you can see as the system becomes sluggish, you're seeing more and more messages and prompts queuing up in the system. So again, you're going to want to look at this when you're self-hosting an LLM and you're thinking about how you scale your system, how many GPUs you're going to need to size it for, and when you're going to need to add more GPUs to the system as you add more users and anticipate more prompts arriving in parallel. Another piece of analysis is regional variability in the cloud. So here we ran the same model, same data, same prompts in two separate regions. We did it over three runs, and what we're able to see is that region two has higher response times and also more variable response times. So clearly region one is a better region in which to run this model, where we observed, much better, faster, more stable results. It begs more analysis. It probably begs a call to the hyperscaler to ask them about it. But certainly something you're going to be interested in if you are self-hosting an LLM and managing it yourself in your cloud environment. So that brings me to hidden impacts, and performance of LLM systems can be impacted by things that typically go under the radar. So LLM serving frameworks are probably the unsung heroes of many LLM applications. A model serving framework manages the deployment and operation of LLMs, handles tasks like request distribution, resource allocation, and we compared two of the most popular ones out there, VLLM and TGI, which is by Hugging Face. And again, there's a mixture of different workloads and models in this analysis. We have a short context workload and a long context workload, and we have both 8 billion and 70 billion parameter models. And we're able to observe a subtle but measurable impact, and the choice affects quality, efficiency, and consistency, depending on which platform you choose. So VLLM generally outperforms TGI in terms of inference rate. If you want the maximum number of inferences per second, and you're thinking about latency and throughput, VLLM wins. But TGI delivers more consistent and deterministic responses. So if you care about consistency, TGI is better than VLLM, according to this analysis. Last point here is that the platform version of these things does make a measurable difference as well. And we strongly encourage people to stay on, if not the bleeding edge, the latest stable release of these frameworks as they're getting developed rapidly. I'll finish with a note that all tests in our analysis here use the Stack AI benchmark and test harness, which was defined by the Stack Benchmark Council's AI working group. The Stack Benchmark Council is made up of over 500 financial services institutions, hedge funds, investment banks, exchanges, and brokerages, and supported by a very strong technology ecosystem. So if you want to get involved, three different ways. You scan the QR code on the left, connect with me on LinkedIn. Be delighted to have a chat. Scan the QR code in the middle if you want to join the working group, and scan the QR code on the right if you're already on the Stack Benchmark Council and you want to get access to the benchmark and test harness. So with that, I'd like to say thanks very much for listening and hope everyone has a great weekend ahead. Cheers.